So, good evening. This is our seventh session on fundamentals of electronic materials and devices. So, have you been intimated about any classes that would come outside of 18th or any specific dates? Have they informed yet?
No, I don't. I think they should have. I don't know, but I'm not read through the announcement.
Okay, fine, fine. So, you like our next class is supposed to be on 18th, right?
Mm,
Yeah, so that'll probably get shifted to 19th or 20th, and other than that, we'll be having one more session.
okay.
Yeah, so the one on 18th, I'm kind of busy on 18th, so it will be on 19th or 20th. And there will be one more session on 21st. I had like they had floated a form asking whether I'm willing to take additional classes or not. So in that I had filled for 21. So I was asking whether you guys got any intimation regarding.
No, no, not yet.
Okay.
So it'll be not on 18th, and it'll be on 20 and 21st.
21st, yeah. Like I have opted for 21st, but I haven't received an approval mail from them yet.
Mm,
But in case it is there, you guys will probably get it on the portal or in the announcement section. Yeah.
okay,
Yeah.
that's fine.
So yeah. So that we can start with today's problem. So today we'll discuss questions that is on MOSFETs as well as questions related to the lasers and light part, light absorption. And in the next session, we'll probably go to the photo detectors and solar cells. And the last session will be an overall revision.
Okay,
Yeah, yeah,
yeah.
yeah.
MOSFET is what you said you'll be discussing today, right?
Yeah, yeah, yeah. Like I
Oh,
won't go into the theory today. I'll discuss the questions, and on the last day of revision, we can go to the theory, just so that we can finish it. Yeah. And in case you have any doubts, you can ask that today.
okay. I could
Yeah.
not solve the problems of
Okay,
that.
fine, fine. So we
We
can
can take.
solve that today. Yeah.
Yeah.
Yeah. And one more thing I wanted to ask regarding what was and the formula sheet, the one I had mailed you one before, and
Mm,
one has been uploaded recently in the portal. So just check whether both are same.
okay.
Yeah. Yeah. And since it is already uploaded now, I don't think there won't will be a provision to change. So whatever
Okay.
equations won't come in that, it's better you keep a note of that and try to memorize as far as possible.
Okay.
Yeah. So we'll start with the first question. So we can consider a MOS structure. Consider
Mm-hmm.
a MOS structure using N-type silicon. Using N-type Si, whose ND value is given as 7 into sorry, 7 into yeah 10 power 16 centimeter or minus 3. So what
Mm-hmm.
is the voltage required? You have to find out the voltage required to make the surface intrinsic. That's
Mm-hmm.
the question. Yeah. And the given values are Ni is equal to 10 power 10 centimeter power minus 3. This is 0. And temperature is 300 Kelvin. Yeah. Here you have to find out V to make the surface intrinsic. We know that in MOSFET, since one is a metal component and one is a P-type or N-type semiconductor, and when we bias it, what happens is that initially a depletion region will be found, and when the voltage value goes beyond a particular threshold value, the type of semiconductor gets inverted. Suppose if we were starting with a P-type, or it could converted to N-type or vice versa, right? So
Mm.
here they are asking, it is not getting inverted, but the surface is becoming intrinsic.
What do you mean by intrinsic here?
Intrinsic meaning that there is no additional no additional carriers are there. Whatever was already there, like without any additional doping, what was the amount of like if the number of carriers in the mid at the surface becomes equal to the actual number of carriers in the p-type semiconductor. Sorry, here it is an n-type semiconductor. Yeah, like
Hmm.
usually in MOSFETs we'll say that, right? Surface has a different amount of carriers. In the inversion region it is different. In the depletion region it is different, and
Correct.
in the bulk
Hmm.
it is different, right?
Hmm.
They are
Hmm.
asking what is the voltage at which the surface becomes equivalent to the bulk.
Okay.
That is intrinsic. Because intrinsically it is an n-type semiconductor here, right? So
Hmm.
when does this surface has the same number of carriers as that of the bulk?
So it is an N type now.
It is an
So
n-type now. Yeah.
so there is a depletion region, and that depletion region should become N type, correct?
Yeah. So like usually if it is an n-type, you divide it into three parts. This is there, this is there. Okay. And this is the bulk. This is the n-type, right? Here
Hmm.
the number of carriers is ND. Here it is
Hmm.
ND. And in the initially remember that it was an N type. So here P will be very, very greater. Here P will be less than N. P is less than N, but P is greater than ND. So we have to find out the value voltage at which same ND number of carriers are created on the surface.
N is equal to ND in the bulk. That is
Bulk,
correct.
yeah. So
And
what?
there is another region.
This is the
Uh,
depletion region.
First one is the depletion, or
This
second
is
one
the
is.
inversion region. Inversion.
Okay, that is the inversion region. So here that it should become P, right?
Yeah. This is
And
the
here it
depletion
is
region.
depletion region. Okay.
Okay. They are asking the voltage at which the number of carriers on the surface part becomes equal to ND. So if you
Okay.
see the equation for NS, the number of carriers on the surface, you'll probably get an idea. Yeah.
It is there on the formula sheet.
Let me check. Once a minute. The formula sheet. Some equation, is there any equation for NS?
No, I don't see NS in particular.
Hmm, somebody else has to. No, it's a person. Okay. There is no equation for NS, right?
Mm.
Okay. Only they have most junction. Related to most, they have only one equation, I guess. That is the most junction 5s value. So this is one equation you'll have probably have to keep in your mind. So that is, I'll just show you the equation now. That is NS is equal to NI exponential of phi s minus phi b by kb into t.
Where is this in the textbook also? I don't see
Textbook
one.
page number 129, if you see, you can get it.
Okay, 120.
129. Yeah.
NS is equal to N9 into
Yeah.
exponential. Yes, okay, okay, got it. Yeah.
So now you just go through the question. What does the question demand? They have given that the voltage required to make the surface voltage, let us say we'll get value of, we need 5s value, right?
Yeah, 5S, we have an equation.
Yeah. So but that particular equation we can't use, but that because that has permittivity of free space,
Yeah.
then
Yeah.
Na, WD, all those things. So you will have to start from here in this question.
Mm. NS
Yeah.
is
So here,
NS.
yeah,
So when you mean NS, what does it mean? One second.
number of
Surface
carriers.
concentration.
Yeah,
Concentration of N at the
carriers on
surface,
the
right?
surface. Yeah.
Yeah, N exponential. But we don't have 5S and 5B also.
No, you'll come to that. Like if you start solving, eventually you'll come to that.
So we have only Ni here. KBT is there. So you want me to calculate 5S minus 5B?
Yeah. Before that, if you substitute Ns is equal to Ni, what will you get? Suppose here it is said that you need to make the number of carriers on the surface equal to that on the bulk. So which means that Ns is equal to Ni, right?
And S is equal to
To
Ni.
Ni.
Correct,
That is our
correct, correct.
condition. Yeah.
Mm-hmm.
So if Ns is equal to Ni, then 1 is equal to exponential of this part.
Exponential of 5.
So if you take ln on both sides, it will become, this part will become 0.
0.
Yeah, so then phi s will become phi b, right?
5S will become
phi s is equal to phi b will be the condition that we get.
Phi s is equal to phi b,
Yeah,
correct.
which means that the potential on the surface is equal to potential in the bulk.
Hmm. Hmm.
And now we have an equation for finding phi b. That is also not mentioned here in your formula book. That
Okay.
is kb t ln nd by ni.
Where is this on the?
Textbook, if you see equation 8.6, you can see that phi
Okay,
s is
yeah.
equal to 2
Is
times
equal
phi
to
b, which
2
in
pi
which
r.
phi b is kb is equal to t ln na by ni. Here they are talking
Yeah,
about the
you
p
just
type.
remember this.
Yeah,
Okay, that's why can't this be included in the formula sheet if it is
it
required?
should have been, but maybe I don't
Probably they
know.
should go ahead and do that now also.
Yeah, I'll ask them, but yeah, since it's already up, maybe they can change and
They
upload.
can upload it again, right? How
Yeah,
much they
yeah,
have a lot of time till the exam gets.
yeah. So I'll ask them to upload like 8.3
Please.
and 8.6 is actually required multiple times, but 8.3, 8.4, like all of those can be included actually.
Because remembering would be difficult.
Yeah,
So much questions. I don't
yeah.
think it is really plausible.
So you get the whole idea right now. Can you just go through the question again and see if you
Yeah,
can?
consider the monomer structure and type and this voltage required to make the surface. Yeah. So they want us to calculate the voltage, right?
Yeah,
Phi B is equal to KBT ln of ND upon NI. Okay, so phi B is going to be the voltage for.
yeah. They have asked us to find the potential voltage or the potential required to make the surface intrinsic. So the phi b and phi s are the values that we give as potential, right? So we have to calculate that value.
Okay.
Yeah. And now going to the equation
Calculate
part. Yeah.
phi B.
Yeah,
Okay.
phi b we can find out.
So 1 second, let me understand what is phi B. I read through this, but there's a lot of.
Yeah, sure, sure.
1 second. So what is phi B? Just if you can.
Phi b is potential. Suppose in the MOSFET, if you see in the like semiconductor material,
I
there is
thought
one.
you will explain it,
Yeah.
so I could. I did not revise this. This is
Okay.
almost a week back, so
Okay. So
you can
basically,
just go
yeah,
through the uh,
basic thing. Yeah.
basic part of MOSFET, just simple explanation, so that will help us
Okay.
solve it the way it will be. I thought because last time we discussed the
Yeah,
PN,
yeah, yeah.
right? So I thought you will do that. So I did not
Okay,
read
fine, fine.
through
So basically, just saying this, like say, suppose you have a MOSFET.
it.
Here you have a P-type material. There are two N-type material and so on and
Correct.
so forth, right? And there is the depletion region part and all those
Mm,
things.
mm, mm.
And initially, if you see the junction between these two things, the P and the N part, initially what happens is that suppose we have that material, initially we have a depletion region,
Correct.
right? And this is because of the applied voltage, the voltage we are applying across the gate,
Mm,
right?
mm,
So what happens is that as we go on increasing this potential, and when this goes beyond a particular value called as the threshold value,
mm.
what
It
happens
becomes
is it
N.
becomes, yeah, the P
Mm,
becomes the N type in the small region here,
mm,
and
mm,
the rest remains P.
mm.
So because of this difference in carriers itself, the potential on the surface is different from the potential in the bulk.
Correct. Okay,
Yeah,
got it. Mm,
yeah.
mm.
So that is the value they are asking. What is that phi is we want, such that here it is not going into the inverted part, it is just becoming same as that of the bulk.
Mm,
Yeah.
mm.
So we have to find the phi s value.
Okay.
Yeah.
It is only for the P, right? But the other two, just come a little bit down.
Yeah. Yeah.
If you have. So you made this two smaller P's, N's,
Yeah.
right?
Yeah.
Yeah. So those are N's. So we want to convert that top part only. So when we alter the voltage between the gain and the source and the
Yeah.
um,
Initially there will be an N channel here. and
Correct,
because
correct,
of which
correct,
the electrons will flow from the
correct.
source to drain.
So, yeah,
And when we
yeah.
change these the gate, and
Voltage, yeah, gate,
what
correct.
happens is that as what happened in JFIT will happen here also. The
Correct, correct.
channel will pinch off and the
Yeah,
value
but
becomes
here
constant.
it is happening because of the voltage
Yes,
manipulation.
yes,
In
there it was
JFET,
intrinsically there,
there was,
here we are
yeah,
manipulating the
manip.
applied part.
Correct. Got it.
Yeah,
Okay, clear.
that's the
Thank you.
only difference. Yeah, so now if you see, they have just asked what is the phi s value, and
Hmm.
because of this particular condition ns is equal to ni, our phi s
Hmm.
here is equal to phi b, and we know the
Right.
equation for phi b.
Correct.
Yeah, now can you just substitute and tell me?
Yeah.
Yeah.
So should we do the substitution? I think I was thinking we
Yeah,
solve
no,
more
no.
questions. I think the substitution can be done. I am used to the calculator now.
Okay,
It is more
no,
of
like
KBT ln of ND upon NI, right? That's
mm,
the 5.
yeah, that
I'm
is the thing, but it's instructed to make students solve. That's why I'm really sorry, but it would be good if you can solve. Yeah.
I really don't want to waste time, but yes,
No,
I
no,
can
it's
do
okay,
that.
fine, fine.
Ln of ND by NI. What is ND? Is 10 raised to
7 into 10 power 16.
7 into 10 raised to 16. Right?
Yeah. P is 300, then
NI is 10 raised to 10.
and rest 10 power 10, yes.
T is 300, right?
Yeah.
Is it 6525.22 into 10 raised to minus 23?
No, the thing is, if you see the options for this particular question, it is given as 0.41, 0.61, 0.82, and
Hmm.
1.04. So can you tell me why that would be?
Is there any changing of units?
Yes.
Okay. What is that we had to change? ND is also in NDNI
Yeah,
and
NDNI
T
is fine because since it is a like,
ratio.
yeah, it's fine.
Mm,
But here, if you see, we substituted kb in joules, right?
correct. Joules
So
per Kelvin.
yeah, so whatever we are getting is an energy value that has to be divided with 1.6 into 10 power minus 19 to get the volt value,
Okay,
two
okay.
electron volts. So then you'll get nearly, can you just check?
Let me do that
Yeah.
one. Equal to is it 4.1?
Yes,
0.41? Yeah.
0.41 is the answer. So, all these five inversion, strong inversion, all these kinds of questions, either you have to substitute kb
Hmm.
in electron volt value, or you have to do it as joule and then divide by 1.6 into 10 power minus 19.
Yeah, got
Yeah.
it.
So next is now they have asked same thing. Suppose you want to create strong inversion at the surface. Same question, same detail. Strong inversion at surface. Initially, they wanted to find the voltage at the surface to make the surface intrinsic, right?
Hmm.
Now they want to get the voltage to make the surface strongly inverted,
Hmm.
which means that the like whatever number of carriers here becomes equal to ND, like much greater than but in the opposite sign.
It has to change. It has to
Yeah,
become N. Yeah.
yeah. So what is the potential? So there is a condition 5s is equal to, can you, if you remember the condition?
5 is equal to 2 5b.
Yeah,
Can you
5s is
explain?
equal to 2 times 5b. That is the condition for strong inversion.
Mm,
5s is equal to 2 times of 5b. So we have already found out that 5b is equal to 5s is equal to
uh,
0.41, right? So it will just
mm,
be 0.82.
okay.
Yeah,
Just come to the previous one.
yeah.
The first question we solved was okay. Uh,
Intrinsic.
ND.
Yeah,
ND is
like
when you
the
have
first
N
question
type,
was
right?
n is equal to ni. Now we are solved for n is equal to nd.
Uh,
Yeah,
Come again to the top.
yeah.
So here in the first question, we were asked to solve, consider N types and voltage required to make the surface intrinsic.
Intrinsic. Ns there became ni, right? Here ns has to become nd. First one was ns equal to ni, then n is equal to nd.
When you mean Ni,
Yeah, intrinsic
uh,
carrier concentration.
what does that mean? Ns is equal to Ni. I'm not able
Like
to.
whatever number of carriers are there on the surface is equal to number of carriers in the intrinsic semiconductor without any doping or anything. This Nd will get after doping it with some kind of electron rich material,
Okay,
right?
so if it is P, then there also they want a P.
Yeah, if it is, suppose you want to make it, see, this is a, they have told it's an N type, right?
N type, right? Yeah.
Yeah, then Ns is equal to Ni will be the first condition and Ns is equal to Na will be the second one. Yeah.
When you mean Ns is equal to Ni,
Hmm.
just come up to
Yeah,
the
I'll draw two things. So this is my intrinsic one
correct
and
intrinsic
this
one.
is my extrinsic semiconductor.
Correct.
So
So
here
when you
what happened is there are only Ni number of carriers.
correct,
Here what happens is to Ni, I'm adding some, so suppose you want an N type semiconductor, N type and extrinsic, then you're adding electrons, lots of
correct.
electrons.
So it becomes Nd. You did
Yeah,
donor.
yeah,
Yeah, you did Nd there.
yeah. So, and the question is, I have a MOSFET here. This
Uh,
is my MOSFET
Correct.
and this is the surface.
Correct.
So in
So
the,
this is a MOSFET with what type? This is a MOSFET with N, right, at the base?
yeah,
Because they gave that it is an ND, right?
yeah,
They told that it's an
yeah.
N type.
Whether it is N type or like in the case of MOSFET, whether it is N type or P type, inversion means that it just becomes volta. If it is N type, surface becomes
It
P at
becomes P.
strong inversion.
Correct.
Yeah,
Correct. Correct.
yeah,
But I'm asking you now.
yeah,
The first question was when they said intrinsic, then
yeah.
N they wanted to make it Ni. They wanted to make it N. N and N should be there. That's what they wanted, right? At the
Let
surface.
us call the number of carriers on the surface as Ns.
NS. Okay.
So
Correct.
Ns is equal to Ni was the thing that we wanted initially.
Correct. So NS also should be N only, no? Because if no voltage is applied,
Huh?
it is already NS. N is equal to
No, when
NS.
we talk about MOSFET, these three things have different meanings. Like Ni is intrinsic, N
Correct.
is number of a region where there are excess of electrons, but it is not equal to Nd. Nd is the
Oh,
maximum. So this is
hmm.
something that lies in between.
Okay.
Yeah. And usually they'll give the Nd value for inversion because it just
Oh,
becomes ulta, right? Here
okay.
we can't use N because if you see inversion part, then you have the depletion part and you have Nd. Here the concentration is Nd, here it is N, and here it is
Hmm.
Ns. So this is that intermediate region. There are more electrons here, but not as high as Nd.
Hmm.
Yeah,
Hmm.
that is what they mean.
And in the top, it is complete inversion,
Yeah,
NS.
like it
Oh,
becomes ulta. Whatever here it was Nd, same number,
then
but it becomes
NA.
Na.
NA. Okay, got
Yeah,
it.
yeah,
Okay,
yeah.
we can go to the next one.
Yeah, then okay, now in the assignment there were few questions, right? We can solve. You can just see whether those are the same or not.
Yeah, I'll just read through that.
Yeah.
I could not solve one second.
Which one was it? If you can.
I
Sentence.
could not solve most of the problem once there.
Okay.
Consider, yeah, I'll read
Yeah.
few.
No, no, I have the questions with me, so we can see the problems one by one. Theoretical ones are fine, right? Because we had
Yeah,
solved in
theoretical
class.
ones were simple. The
Yeah.
problem ones were little bit.
Okay, the first one is consider an N-type MOS. It is an N-type MOS with the donor concentration. It is an N-type MOS with the donor concentration is equal to 4 into 10 power 16, and intrinsic carrier concentration Ni is equal to 10 power 10, okay, 10 centimeter inverse. If the surface is biased such that there is strong inversion. This is a misleading question, I would say, because they have used the word donor, but it actually means that what contributes to the conductivity. So this is ND itself, whatever they have given. Yeah,
Sorry, 1 second. Let me read it again.
yeah, yeah.
Consider n-type MOSFET with a donor concentration of 4 into 10 raised to 1.
Yeah,
Okay. And
electrons.
intrinsic
Yeah,
content, the surface is biased such that it is
this
a
is strong
strong inversion.
inversion. Yeah, the same
That
condition that
becomes
we discussed here.
Na, it becomes, right?
Yeah,
What is the electron concentration at the surface? Then it's the same, right? 4 into 10 raised to 16.
yeah. They have asked there is strong inversion. What is the electron concentration at the surface? Okay, now it is an N type, right? So
Correct. Now
initially,
presently
my
it is n-type. It
yeah,
will convert to p-type at the surface.
yeah, they have asked the electron concentration in the surface while inversion happens, holes are Na, right?
Correct.
So we have to find the Ns value. That is what they are asking. So initially we have a MOS, it was N type.
Correct.
And
Okay.
at strong inversion, what happens? This region becomes P type.
Correct.
P type has more holes.
Correct.
It has less electrons.
Correct.
That less electron is what they want to know.
So how do I get that?
So first we it is give what all are given to you.
I answered the same. I think I got confused and put the same number as 4
4
into
into
10.
10 power 16, right?
That is wrong.
Yeah, we have to go. There was a like NP is equal to Ni square was there, right?
Nice. Yes.
Yeah, we have to go through that route. Yeah, if they were asking the donor concentration at the surface, the same value is correct. Sorry,
Okay.
acceptor concentration at the surface, that was correct. Whatever holes, because it becomes P type and it has the same number of holes.
Mm-hmm.
Like ND in the bulk becomes Na on the surface, so the same value 4 into 10 power 16. But they are asking what is the minority part there.
P, they are asking the N, sorry,
Electron,
N.
yeah, the electron part
Because
they are asking.
N, how much, how do I get Ni here? Because they have given Ni?
They have given Ni, let me check.
Yeah, they have given 10
Yeah,
into
they
10.
have given Ni. Yeah.
Okay,
So
10.
first
So
you
let me
have to
10 raised
find,
to 10.
yeah,
Yeah.
holes at the
So
surface.
holes is the same, right? It will be 4 into 10 raised to 16.
4 into holes at the surface, yeah. 4 into 10 power 16.
So divided by 10 raised to 10.
Yeah. Then they what we have to do is that 10 power 20 divided by 4 into 10 power 16. That is what we want.
Okay, let me do that.
Yeah. Divided by
10 raised to 10 divided by uh, 4 into
10 power 16. Now you have one of the options. Like it matches with one of the options.
no, it doesn't.
Um,
I got the same 4 into 10 raised to 16. I got no answer.
how? See,
10 raised to 10
we
divided.
have to find the number of electrons on the surface. So it is what? N A. This was P or N type. Okay, say
Yes,
ND, right? Na divided by Ni square. Sorry, Ni square divided by Na.
correct. Ni square. So 10
So
raised
10,
to 10, 10
20
raised to 20.
divided by 4
Oh, 10
into
raised to
10 power
20. It
16.
did the wrong. One
Yeah,
second.
yeah,
I think I did calculation error. Let me check.
yeah,
1 second.
sure.
Yeah, I got the same answer. 4 into 10 raised to 16 only.
Uh, 10 power 20 divided by 4 into 10 power 16.
Yeah.
How
10
come?
raised to 20 divided by 4
10
into
power
10 raised to
4. You
16 is
will get,
4 into 10 raised to 16.
yeah, you will get divided 10 power 4 divided by 4, right? 10 power 4 divided by 4 will be 2500, right?
1 second. Don't know where it is going wrong. I think
Okay.
I'm doing it this bracket. I think it is not taking right.
Okay.
Okay, correct. 2000. The options are 2000, 2.5 into 10 raised to 3.
Yeah, 2.5 into 10 power 3.
Okay.
Yeah.
Okay. I think I missed that. I no, I had made the same mistake of 4 into 10 raised to 16. Thinking it was they are asking the holes only, so I did not read it was electron. So yeah. Okay, correct.
Yeah. So
It's fine.
now can you just read through the question and see if while reading itself it is clear?
It's clear. I got the sixth one, no problem.
Yeah. So next.
Move to the next one. Consider 11th one.
Okay.
Consider mass structure as this is what we solved, I think.
Consider
11th is
what is required. Yeah, make the surface intrinsic. And
yeah.
just 0.41. Yeah.
13th is what I'm
The
looking.
same thing, strong
Oh,
inversion.
okay, okay. This also we solved.
Solved. Yeah.
Okay, let
And
me
then,
take the 14th one. 14th also. In N-type gallium arsenide mass
yeah.
at the end, the donor concentration is 2 into 10 raised to 16%. My intrinsic carrier concentration is 20.
Yeah. Like
Calculate
whatever we discussed so far, all
electronic
of that is included. So can you try solving?
at the surface during strong inversion.
Yeah. Like the two questions were there, right? Np is equal to ni square as well as phi s is equal to 2 times phi b. Both are required here. So if you, like, so far
In
if you have
the
understood, it
donor
would be easy.
concentration and the intrinsic carrier concentration is calculate the hole and the electronic. Yeah, they're asking for both of them
Yeah.
during strong inversion, right?
Yeah.
During strong inversion, the donor it will be 2 into 10 raised to 16 um, holes, correct?
Yeah.
And I have to calculate the electrons now by ni square divided by that 2 into 10 raised to 16.
Yeah.
We do that. To
So one is 2 into 10 power 16. So that is the whole concentration. That is done.
that is the whole
Now
concentration. So
electron
now I have to do
concentration has to be
ni
found out.
square divided by 2 into 10 raised to 16. So ni square is 2 into 10 raised to 6, the whole square, right?
Centimeter, like, yeah, 2 into 10 power 60. Ni
6,
square by, it becomes
2
what
into
is
10 raised to 6. Intrinsic carrier
2
concentration
into
is,
10 power 6, the whole square, divided
yeah,
by
2 into 10 raised to 16.
10 raised to 16. Yeah. 4 into 10 power 12.
4 into 10 raised
4 into
to
10 power
12
60. Yeah.
divided by 2 into 10 raised to 16, correct?
Yeah. 2 into 10 power minus 4.
Yeah.
Yeah.
Okay, got it.
Yeah. In case they ask
Yes.
for potential,
Yeah,
you
it
have
would
to
have
solve.
helped if you would have solved it before this class. You would have got some
Yeah.
marks.
Yeah. No, like last class you had asked, though I thought like when I gave the
No, I
hints,
didn't
yeah.
get time. What happens is
Okay.
on the weekend, if I don't solve and today, then gone. Tomorrow onwards, week is not
Okay.
in my control. It's with
Okay.
other people. So time is today also. I have to this 1 hour. I just take out somewhere, come
Okay.
home early, and then log in for the later nights.
Okay.
So this is the only day I get to study. Otherwise, it
Study
is a
this. Yeah.
weekend only, Saturday or Sunday. Okay.
Okay.
Consider a P-type semiconductor mass at 300 K. Last one I'm reading
Yeah.
now. Consider P-type mass at 300 with an accepted concentration of 200. The intrinsic carry concentration is this much, and a dielectric constant for silicon is this much. What is the total depletion width at strong inversion? So this, I think, we have this answer question formula here. I think, right?
Yeah.
And let me read here.
You have to find out WM. epsilon 0, epsilon r, then k, t, ln, na, ni, e square by n. Everything is given. You just have to find Wm.
Yeah, but what is the formula? I see here only one formula which is given as phi s e
Okay.
square na, but I have no phi s, right?
Okay, that is, let me check formula sheet.
I think there is another equation in the textbook probably.
In the textbook, yeah, in the textbook it is there directly 8.7.
8.7. Let me read. Yeah. 8.7 we have to use. Yeah. WM. Yeah. But this equation is not there in the sheet again.
Sheet, yeah. What is there is the 5s part, right?
Yeah.
But
But we don't have
actually,
phi.
if you substitute 5s is equal to uh, 2 times 5b, then
But I don't have any of phi s or phi b.
okay, but 5b is comparatively easier to memorize. It is just kb t ln na by ni, right?
Yeah.
Yeah.
There's a lot of
So
confusion now with all the chapters going
5s
in.
is equal to 2 times 5b. And if this 5s you can substitute in the equation that is given to you, then you might be able to solve. And 2 into k b t ln na by ni is equal to e square na wd square divided by 2 times epsilon 0 epsilon r. So you'll get wd.
Okay.
Yeah, the 8.7 is just a condensed version of this.
Yeah.
Yeah,
But
most and
mm,
some things will cut off. Yeah,
okay,
yeah,
it would have been better if they add this equation
yeah.
also.
So it's kind of a
If they're giving
complicated
everything
equation,
on
right?
the exam, then I
Yeah,
know some things might miss here and there, but it would help if most of the equations
questions
are
are
there.
given. So yeah, I'll ask them regard. So can you just try substituting this since it is a bit of a complicated equation?
Yeah. So you're 8.7 only, right?
Yeah,
Why did you bring WD there?
WD is the width part, like WD or WM or just W. You can call it whatever you like. W is the width, depletion width we have to find that strong inversion. That is the question, right?
Okay.
Yeah,
So you used a different equation to that.
yeah.
Okay. So epsilon not epsilon r is not given, no?
Yeah, it is epsilon 0 is like a
Zero is silicon
constant.
is 11.9 only,
Yeah,
right? Both
epsilon r is
multiple.
11.9, epsilon 0 is 8.85 into 10
Okay,
power
the
minus
equation.
12.
Okay.
Yeah.
Epsilon naught is given in the sheet, I think, yeah. 2.2 something. Let me see the options.
Um,
Is it 220?
yeah, it's 220.
Okay.
Yeah. So, any other question related to MOSFETs? Yeah, question number 10, you got the answer, right?
10, 1 second. Let me see what is 10. 10 is. Yeah, 10 we got. No
Yeah,
problem. Yeah.
okay. Then B channel MOSFET, yeah, all those things are done, right? Yeah. So then maybe we can go to week 7. Any other questions you have, doubts? Yeah, in MOSFETs, the maximum problem wise they would ask is one is finding phi S and phi B. Another thing
Got it.
is finding the number of carriers at the surface, at the bulk, etc. etc. And one
Yeah.
is width. Only these three options are there. I'll
Now I
just,
think if we
yeah, I'll,
do this
yeah.
same exercise again, I think it should give us some confidence. Yeah.
Yeah, yeah. And one more thing, what all equations do you like? Can you just check and tell me what all equations you want to add into the formula sheet from page 129?
Yeah, it
Yeah,
is 8.7
8.7. Yeah,
and then
8.6 is it there in your strong inversion?
8.6 also is not there.
Okay, 8.6. Then
8.6, 8.7, 8.3,
okay,
and then you can add also the last one, 8.8.
8.8. What is it? It gives n channel width
Calculate the width
related to
of the inversion region of the n
okay.
channel.
So one, two, three. These four equations, right?
Yeah.
Yeah, so and from the equation 8.6, you can read on what is 5b, right? KBT ln Na by Ni.
From equation,
8.6 itself, what is 5b is clear, right? 5b is equal to KBT ln Na by Ni.
that is two. Yeah,
Yeah,
that
yeah,
is okay.
yeah, like, yeah. Okay, so these four,
If they give either of them, they can specify the full thing. 5s is equal to 2, 5b is known.
yeah,
Yeah, then it's fine.
yeah, so okay. So these four equations I'll ask them.
Hmm.
Yeah. Anything else from week
No, no problem. I think. Yeah, let me check on the week seventh
7?
question.
Okay.
I have done some content on that, so let's
Okay.
see.
And like first, we discuss a few questions from week 7 directly, and then we can move on.
Yeah, yeah, we can do that.
Okay. So let me check week 7 content. Yeah, it's somewhat interesting. I feel it's more interesting, at least for me.
Yeah, now it become too much for us, wherein lot of things happening. So
Yeah.
where you have to really, it's good. Those lectures are good. I don't deny, but now,
Yeah. It keeps getting
it's too.
saturated towards the
Yeah,
end.
in the sense it's too many things now on the same subject.
Yeah.
It's good session, no doubt.
Okay. So first thing is, do you remember from the lectures what is the Beer-Lambert's law?
Yeah,
Okay. So we'll do a question based on the Beer-Lambert's law.
Beer-Lambert's law said the same thing, right? The
Yeah.
incident light reduces with the absorption with the thickness.
Yeah. And it also depends on something known as the absorption coefficient, which is a material specific thing. This
Mm-hmm.
alpha part, extent to which the number of photons are lost in a material is just decided by this thing, this absorption coefficient.
Mm.
Yeah. So suppose it is given that absorption coefficient or alpha is 2 into 10 power minus 5 centimeter inverse, and thickness of our material or semiconductor or whatever is 100 nanometers.
Mm.
Then if I0 is the incident
Incident.
intensity, what is the intensity of light coming out? What is I? So just the relation between these two, can you give me? It is given that alpha is also given to you, thickness is given to you. We know that
Yeah, you have to
Beer-Lambert's law.
calculate I, right?
Yeah,
The
yeah.
same substitution
Yeah,
here.
just a substitution. Only thing is just take care of the units.
Mm. Yeah, yeah,
Yeah.
that's okay. You want to substitute it now?
Yeah, you can try now. Yeah.
So I naught is I naught is not given, no?
I don't know, no need of the value, just want the relation. How is I and I not related? Like I is equal to some constant value I naught. What is that constant value? Just for substitution sake.
Oh, you want the constant value.
Yeah.
You want only us to multiply the exponential
And
alpha and
yeah, exponent of minus so and so. Yeah.
okay. Minus alpha is 2 into 10 raised to 5 into 100 nanometers. Okay. 0.002.
0.002 is not the answer. Yeah.
100 nanometers, right? You want
Yeah.
us to 10 raised to 9?
Okay. The thing is, the options will be given such that I zero. They have asked what is I.
Got it, got it. Yeah, I
Yeah.
got it.
So
I
B
think
is
I.
0.25 I zero. C is
Oh,
0.14.
exponential was there, right?
Yeah.
Okay, one second.
And D
I
is
did.
0.03 I zero.
One second, let
Yeah.
me do that again. Edit the exponent. So we have to convert both into centimeter or something or nanometer.
I'm sorry.
And because I'm getting 2.718.
Okay, so have you noticed that one is inverse and one is 10 nanometer? So that is the
Correct.
reason, yeah, why you are not getting it.
So what is that we have to convert now?
One
Because
is 2 into 10 power minus 5. So which means, and centimeter is in the denominator, right? So to convert centimeter into meter, we'll have to do 10 power minus 2,
correct,
right? So here we have to do 10 power minus 2. So when it goes to the top, it becomes 10 power 2, right?
correct.
Yeah, so this is plus. There is one small mistake I did. Yeah, so into 10 power 2.
Hmm.
This goes 10 power 2 into 100 into 10 power minus 9.
Just minus 9.
Yeah,
Raised to e.
yeah. E raised to this much things. This is plus 5.
Why plus 5 minus
No,
5?
that was my mistake. No, okay. If
Sorry.
it is like
Okay, okay.
minus 5 also fine, but it won't come to these values. Yeah, that was my mistake. Yeah, I wrote.
No, no problem.
Yeah.
That's fine. Okay.
Yeah, so what is the value you are getting?
So if you go by this equation of yours, plus 5 minus 9 plus 2
Okay, so something near to that.
2
Like what is very near to
that
that?
is to minus 3, it is below or nothing?
Sorry?
Oh, e raised to, right?
Yeah.
Okay, one.
Shift
E raised to
in
10.
power. 2 into 10 power 7 into 100 into 10 power minus 9 to be
I'm getting 7.3. Something wrong I did.
okay, but you got the idea right. You can check that later.
Yeah, but what was the answer?
Yeah, it comes 0.14.
Mm.
Yeah. So next is what is the difference between direct and indirect band gap semiconductor?
Direct band gap is when there is
Okay.
photon emission. In indirect band gap, there is lattice heat,
Yeah.
which
So
is
in case of direct, there is only photon emission, right?
correct. Yeah.
So in case of indirect, it is both photon and phonon.
Yeah.
Phonon is due to the heat part, like lattice vibration related heat part.
Correct.
Yeah.
So there is no photon, right? There is only phonon.
No, there will be both.
I thought there is no
No, no.
photon.
In case of direct, there will be contribution from both.
Indirect,
Yeah. In
indirect.
case of indirect, yeah.
Okay, there is also a photon sometimes possible in
No,
indirect.
like indirect majority, like in direct majority is due to photon, in indirect majority is due to the heat part. There will be small amount of this. That's all.
So there might be some
Yeah.
fabrication which they have done where indirect also emits photon.
Yeah, there are, I guess. I've never heard it is only phonon. It's like combination of both, but majority is due to phonons. Like when recombination happens, it goes as both heat and light, but heat is the major component.
Okay.
Yeah.
So my question was, are there any indirect band gap semiconductors which
Yeah,
emit
there are plenty. Like, yeah,
photon?
yeah,
Okay.
yeah, there are. Yeah. Yeah. So next is okay. It's kind of a big question, but still, it's a good question, I think. Yeah. So there is an N-type silicon
Mhm.
semiconductor with say dopant concentration of 5 into 10 power 15 centimeter power minus 3. It is illuminated such that 10 power 21 electron hole pairs are created
Okay.
per cm inverse per second,
Mhm.
and minority carrier lifetime is 50 nanoseconds. At steady state,
Mhm.
what is the ratio of hole to electron
Okay.
concentration in the semiconductor at 300 Kelvin? And Ni is given as 10 power 10 cm power minus 3.
I don't find any equation on the.
Okay, it's more of a logical question, I would say.
Okay, N-type semiconductor with a dopant concentration of this much, it is illuminated
Yeah,
such that 10 to 21 electron hole created
per
percent.
centimeter and per second. And minority lifetime is also given. At steady state, such that electron hole pairs are generated, they stay for 50 nanoseconds and then recombine.
Mm,
What is the ratio of holes to electrons in that semiconductor of 300 Kelvin? Yeah. Initially, you have an N-type semiconductor. So it
correct.
has Nd is equal to so and so, and Ni is equal to so and so. At
Correct.
300 Kelvin, you are shining a particular amount of light
Okay.
onto it.
Then there is a increase, both of them increase.
Yeah, there is more of holes and more of electrons created.
Correct.
Now they are asking what is the ratio of the new N and P. What is the ratio of N and P after this shining and everything happens?
N is 5 into 10 raised to 15 plus
Yeah, plus,
10 raised to 21, right? What was that
yeah,
number?
10 raised to 21. That part is correct, but you have to remember 10 raised to 21 is per centimeter inverse per second. For to find the steady state value, you have to remove the time part from it, right? So you have to multiply it with the lifetime of these electrons
Okay, into 50
into 50 into 10 power minus 9 because it is in nanoseconds. So
nanosecond.
that is
Okay.
your new N.
Correct, correct.
Now you have to find your new P
It is the same again. P is Ni square divided
by
by
ND plus
Nd plus
the delta P.
delta P into 50
Yeah, yeah.
nanoseconds, whatever.
So can you just calculate and tell me what is the final ratio? Like now that you have said it one time, just think of it and note down whatever you understood and just solve it.
Yeah.
Yeah.
One second. Give me a minute. Somebody's knocking at
Yeah, sure.
Yeah, I'll just tell the substitution,
Yeah,
how it looks like. I'll solve it.
yeah.
5 into 10 raised to 15
Mm.
plus 10 raised to 21 into 50 into 10 raised to minus 9. That's how it is.
Okay, first one is new electron concentration. Delta N, what is the value you put? 5.
No, I'm just calculating everything, right?
Oh.
Here they want not only delta n, right? They
Yeah,
want the total concentration,
like
right? So
ND
I just
is 5 into 10 power 15.
15,
Delta N is equal to delta P is equal to 10 power 21 into
21,
50 into 10 power
50
minus
into 10
9.
raised to minus 9, correct?
21, 9 will become
21.
5 into 10 power 13, I think. This is 21, 22, 22 minus 9, right?
Correct.
Yeah. So that is there. Now your new N is ND plus delta N. That is 5 into 10 power 15 plus
Yeah.
5 into 10 power
5
13.
into 10 raised to 13,
Yeah.
correct?
And your new P would be
New Ni square divided by
5 into 10 power 15
10 raised to
plus
minus
5
15,
into 10 power
5
13.
into 10 power 13, correct?
And now you have to find out the P by N value.
Yeah.
Yeah. So this is what you have to solve. The
Yes.
concept is clear, right?
Yeah. I
Okay.
think
Okay.
I'll do the substitution.
Okay.
Take some time.
Now, if they are asking, do you want to have some water or something? You can go and have. It's
Yeah, give me a
yeah,
moment.
sure.
Yeah, sorry.
Yeah. Then neutron and hole are. It says question on similar lines, but here instead of the final concentrations, they have asked for the change in conductivity. So in a steady state illumination, 10 percentage, like 10 power 16 centimeter inverse electron hole pairs are created in an intrinsic semiconductor sample. Initial mobilities are given and Ni is given as 10 power 10 centimeter power minus 3. What is the conductivity under illumination? What is sigma under illumination? That is the question.
Mm-hmm.
Yeah. So
At 16, then is 16 pairs are created in intrinsic. Okay, what is the conductivity equation? This should come in the first chapter or the
yeah,
second chapter.
n sigma is equal to NIE mu E plus mu H.
Nu E plus.
H,
Yeah.
yeah.
So you have to do the same thing. They have given most of it.
Yeah.
Okay. So 10 raised to 16 into
Here lifetime doesn't matter because they have given what happens per centimeter per minus 3,
correct.
not per second.
So to find the conductivity,
Yeah.
I need
The new
electron concentration of electrons into mobility of electrons plus concentration of holes into mobility of
holes. Yeah.
holes, right? So I know that it is 10 raised to 16,
Yeah. Now you have to.
but why did they give Ni then?
That is the thing. There we had an extrinsic semiconductor sample, right? So upon illumination, what happens is that already we had added certain amount of conductors. In addition to that, the new carriers and holes get generated, right?
Correct.
Yeah. Here we are talking about an intrinsic semiconductor. In
Correct.
the intrinsic semiconductor is what is like without any external doping, anything else, Ni was there.
Mm-hmm.
Here, while shining light, what happens is that the new electron hole pairs are not added to Ni, it replaces the Ni.
Hmm.
Yeah. So instead
So
of
it is
Ni,
10
you
to
have to
16.
substitute
Okay.
delta N or delta
Delta.
P.
Okay.
Yeah.
10 is to 16 into 450 and 10 is to 16 into 1350.
Yeah. That is what you have to do. And finally, you have to multiply these with the electron conductivity 1.6 into 10 power minus 19 and you'll get the answer.
Okay.
Yeah.
Yeah.
Is that clear? Like the
Yeah.
concept is clear, right?
We can
Yeah.
understand.
So, suppose this is an again logical question. Suppose you have the energy of light E. Suppose you are having light
Mm-hmm.
of energy E and the band gap of the semiconductor is something Eg, and this E
Mm.
was less than Eg. So what happens? Electrons get
No
condensed,
accumulation.
right?
Yeah.
Yeah.
No electron hole pairs are created. It is less than Eg,
No,
right?
no, it's greater than Eg. I'm asking E
Okay.
greater than Eg.
Okay.
Then what happens is it goes to the conduction band.
Correct.
And the remaining part is lost as heat or light or
Heat.
whatever, right?
Correct.
Suppose it is lost as heat. What is that
Correct.
process called?
Thermalization.
Yeah,
Thermal something.
thermalization. Yeah.
Thermalization.
And you know difference between electroluminescence, bioluminescence.
Yeah. Yeah. Yeah.
Yeah. So what like based on what is the source of creating
Source
that?
of
Yeah.
the beam,
Yeah.
it is called, if it is electric field is creating, then it is electroluminous.
Electroluminescence.
If
Yeah.
it is a photon, if it is a light, then it is photoluminous. If it is a gamma ray, it is radioluminous.
Sense and
And
yeah,
then
that's correct.
one more is there.
Yeah. And now
Yeah.
can
Okay.
you tell me
This,
like what is difference
okay.
between
It gets
phosphorescence
complex
and
now.
luminescence?
Sorry.
Phosphorescence and luminescence. There are two
What is the?
difference between
Uh-huh.
one is luminescence, process of luminescence, right? There is a similar process to that. Everything.
Can you repeat? Can you repeat? Sorry, I missed you.
Hello,
Yeah, go ahead.
am I clear? Like it's audible,
Yeah, yeah,
right?
no, it's audible. Yeah.
So there is one more like luminescent. Different processes are there, right?
Correct.
Like luminescence itself, luminescence means that light emission part will happen.
Correct.
In light
Hmm.
emission, there are two types of processes. Can you remember what are those? Like two very related process. One is fluorescence, I would say.
Sure.
Yeah, other is
Fluorescence.
yeah.
Fluorescence. No, I'm not able to.
Fluorescence versus phosphorescence. Have you heard of?
No, it is there in this chapter. I didn't read
Okay,
across.
basically the thing is that there is absorption and then emission of photons happen, right? Yeah,
Correct.
energy is absorbed. The photons go to, like electrons go to the conduction band, and when they lose their
Hmm.
energy, they come back, right? And while
Hmm. Hmm.
coming back, if they give out light,
Yes.
it is
Photon.
luminescence, right?
Luminescence. Yes.
And if it is an immediate process, like as soon as like as soon as they get excited, they come off. It is known as fluorescence.
Spontaneous, right?
Spontaneous, yeah. If it is a
Hmm.
delayed process, it is known as phosphorescence. Yeah, like in
I read only stimulated and spontaneous
okay,
and
fine,
absorbed.
fine, fine. Yeah, it's just an additional thing. Yeah,
Okay.
yeah.
It was. I don't know if it was
No,
covered in
if
this.
it's and if at all a theoretical question is asked, you can.
Yeah.
Yeah,
Yeah. Okay. Got it.
yeah. Then wave like LED part and line width of LEDs. Have you gone
Hmm.
through the
No.
equation? Do you know the line width equation for an LED?
I think I can search the
Yeah,
textbook.
yeah.
I read that. So.
Let me also check the text. Yeah, it is there in page number 155. Line width at full width half maximum for a PN junction LED is given by that equation. Delta lambda.
Delta lambda,
Yeah.
yeah.
So there could be questions where they will give the emission wavelength, that
Mm,
is lambda, and they can give the different temperatures. Rest all are constant in those, right?
correct, yeah.
Yeah, so they can ask the line width at different temperature as well as different emission wavelength.
Okay.
Yeah,
Again, equation is not
not
there.
there. Yeah, yeah. I'll talk to them. Okay. Then
Yeah.
related to internal quantum efficiency, all those things. Have you read through LED
Yeah, I've read through,
efficiency?
but
Yeah.
it's difficult to really remember them.
Okay.
I've
Let,
read them once. I know when you say that now. When I was reading, I understood.
okay. So if you see
Remember,
there is an equation
yeah,
10.8 there, right?
10.8. Yeah, yeah,
Efficiency of external is
yeah.
equal to internal into optical.
Yeah.
That is another possible question where they can give either of these two quantities and ask us to find the third one.
Mm, yeah.
Yeah. Then one more thing is,
As an individual chapter, I can remember, but when
okay.
I mix everything together, I think
Yeah, it becomes difficult.
difficult a little bit.
Okay. Yeah. And the relation between energy and wavelength, you know, right? It is
Yeah.
direct or inverse.
Yeah. Energy and wavelength. Inverse.
Inverse. So they
Yeah.
can give you a set of materials, for example, zinc oxide, cadmium selenide, gallium arsenide, and they can
Mm.
ask you, like, what,
Absorption is also reverse, right?
yeah,
The lower the wavelength, the higher the absorption, right?
absorption, yeah. So they can
Oh.
ask you, like, arrange the following semiconductors in the order of increasing wavelength of emitted light during recombination.
Mm,
Those things can be asked.
correct.
Yeah. Then what is there in this chapter? Let me check. Then basically, what are lasers and what happens during their excitation, emission, and so on and so forth. Yeah, so these are
Yeah.
the generalized things there in like week 7 content. Now you can go through the assignment and then like, tell me what are
Yeah.
your doubts. Yeah.
Let me. I have not done
Yeah, sure.
7
You
still.
can take your time and go
Yeah.
through the questions and tell me.
Sure. Yeah. 9th is okay. We solved it. Similar one.
Okay. Let me check. Okay, one, two, three, four, and all are fine.
8th is fine.
Okay. No,
7.
the and logical
One,
part,
two,
yeah.
three, four. Yeah. 1, 2, 3, 4. I've already done that.
Okay,
Yes,
nine
the
seems.
principal atomic emits the light at the lowest wavelength during recombination. The fourth one is
What I mentioned just now, yeah.
gallium arsenide.
Okay, they have given materials, right? Yeah, first you need to find out the band gap of these things.
Correct, yeah.
So band gap values will be in the order of zinc oxide, GAP, CDSC, GAS. Zinc oxide among these has the largest band gap.
Mm, lowest wavelength during
Yeah, so
recombination.
therefore they will, zinc oxide will give the lowest wavelength. Largest band gap, lowest wavelength. So first you have to find out the value of band gap and then arrange them.
Okay.
Yeah. Then band gap is given as 2.5. Which of the following wavelengths would be absorbed by? Yeah. That can you solve now? It's very easy and it's just a logical question. Question number
Band
5.
gap of a direct band gap semiconductor is 2.5 E. Which of the following wavelength would be absorbed by the material, creating in a node? Okay. 2.5 EV, right? So I need to calculate lambda. Okay. Um, um, HC by
Yeah. Can you calculate
H,
HC by lambda?
HC by lambda.
Yeah.
So E is equal to 2.5 EV HC by lambda, right? So I have to calculate lambda, right?
Yeah.
So lambda is equal to HC divided by EV, 2.5 EV.
Yeah. So lambda value we'll get, right? So what is the lambda value then? Can you just calculate, and then you have to find out from the options what is the values that are absorbed.
1 second. HC is given here, right? H and C constants are given here. Yeah, let me do that. So electron volt also I need to convert into joules, right?
Depends. Like if you are using 1240 by lambda, not required, I would say.
Sorry?
Like whenever you're converting this, right, you can use a shortcut. E is equal to 1240 by lambda.
E is equal to
1240 by lambda. That Hc constant in nanometer and electron volt would become 1240.
okay, 1240 by lambda.
So you
Okay.
have to just do 1240 divided by 2.5.
Yeah, but
Yeah, so you got a value, right?
no, 1 second.
Yeah.
I'm just still calculating.
Or we can go for finding 6.624 into 10 power minus 34 into 3 into 10 power 8 Hc into 1.6 into 10 power minus 19 becomes what is in nanometer.
496 I
Yeah,
got.
496 is the threshold value based on E. So whatever is less than 496 or greater will be absorbed. That is the question. There are two options.
Greater, right?
Can you suppose, see, let me give you an example. Suppose a material has Eg is equal to, say, what is the value here? 2.5, right? Suppose I'm giving energy as Eg is equal to 3, 4, 5, so on and so forth. In all these cases, excitation would happen, right?
Yeah, excitation would happen, but only 2.5 would be absorbed, rest all would.
Yeah, rest all would go, but 2.5, 1240 by 3, 1240 by 4, all of these
What?
wavelengths are absorbed. So wavelength would become lesser, right?
Correct.
Yeah.
Correct.
So then how would you answer that? All wavelengths.
Below.
Yeah, exactly.
Okay.
Yeah.
This is correct.
Yeah.
Right, I think. That's correct.
Yeah.
Good, I think, explanation.
Yeah. So
Okay.
then next question. ITO has an anti-illusion rate which is used at some thickness is given, transparency is given, absorption coefficient. We have to find out alpha.
So I'm in which is used as a transparent conducting oxide.
Thickness is given. We have to find out alpha, and many constants are also given, right? And transparency T is 80 percentage.
But which equation do I use?
If you've gone through the lecture, there would be one that gives absorbance is equal to log of 1 by T. A is equal to log of 1 by T. So first from that you will get A. Check if it is there in the textbook.
Which equation on the textbook?
It's like normal absorption emissions. Okay, that is, I think you can Google a normal basic physics kind of thing. It's not there in the textbook, I think. It's just that you know that whatever light passes through a medium, three things happen. Part of it is absorbed, part of it is transmitted, part of
Mm.
it is reflected, right?
Yeah.
So here reflection is not mentioned, only P and A are there. And there is a relation between A and T. So you can check that part. What is the relationship between absorbance and transmittance?
And there is one question, I think.
Yeah.
Okay.
Yeah.
The next one is consider.
And in that question, one more thing is they have asked for alpha, right? First, you
Correct.
convert your T into A, then you have to find the relationship between A, thickness, and alpha. These three things. There is an equation connecting these three things. It
Okay.
is, I would say, a condensed form of, if you check out normal physics related like literature, you will get the condensed form of the Beer-Lambert's law. Something similar
Mm.
to that. Yeah. You can check that out, and if you don't get it, you can just mail me and then ping me.
Mm.
Yeah. So then,
The seventh one is what? Consider a wide
okay,
band gap
okay.
semiconductor with 3.4 eV photons of wavelength 300 nanometer incident on the semiconductor and the photon flux of this much per second. If every photon is converted into electron hole pair, what is the total heat generated during
Realization.
thermalization?
Yeah.
Where is this equation? See.
Band gap is given, lambda is given, generation of this thing is given. We have to find out the heat due to thermalization, right? So basically, it is an energy value that is related to lambda. So only equation we know based on that is E is equal to hc by lambda.
Correct.
So if only one photon, only single photon is in like only yeah a single photon is there, then E is equal to hc by lambda, right?
Mm.
Then total heat would be whatever we have calculated, that is E is equal to hc by lambda, deducted from the band gap into the generation rate.
No, I didn't.
See,
Sorry.
for one photon energy value, we can get E is equal to hc by lambda, right?
Correct.
Thermalization, what is meant by thermalization? The amount of like,
Yeah, whatever the photons is supplied, it is getting
yeah.
converted into
See,
heat.
suppose you are supplying X amount of energy to it. The
Mm.
material X has some different components A and B.
Mm.
So A is the band gap of material.
Mm.
So after going, what is lost? Like after exciting, what is lost? That is the difference between A and B is what is lost is thermalization, right? Because A is band gap
Mm.
and it has been absorbed by the material. Now only B is left, right?
Mm-hmm.
So this B is what is lost is heat. So here if you say that I have some particular 300 nanometer wavelength light is there with me. If I
Mm-hmm.
convert that into energy value, that would become around, suppose, say some 5
Mm.
electron volt is the total energy I have.
Mm-hmm.
Among that 5, since my band gap is only 3.4, only
Correct.
this much is
5
absorbed.
minus
5 minus
3.7 plus
3.0 is lost as
1.2
heat.
is lost as heat.
Yeah,
Okay.
and that is for one photon. Now they have
1.6.
given the rate as well.
Mm-hmm.
Yeah, so if you multiply that 1 point whatever into the rate, you will get the final answer.
Okay, got it,
Yeah,
got it. Okay, let me try that.
yeah. And some conversion is there, joule to electron volt and all those things
Mm-hmm.
that you have to think about. Like which unit you are substituting this 5, 3.4, all those things. Accordingly, you have to convert your energy value. That hc by lambda value, you have to put in the same unit, whether it is EV or joule.
Mm-hmm.
Yeah, because better to do in joule because finally the answer would come in watts, right? So
Mm-hmm.
better to convert everything to joule and do like all these electron volts you can convert to joule and then start substituting.
Okay.
Yeah.
I think we did the ninth one also, right?
Ninth one, yes, we
Eighth
have
we
done.
did,
Yeah.
ninth also we did.
Yeah.
Let me read. Which of the following statements are true about direct and band gap semiconductor? Note one answer. Indirect band gap semiconductor can be used in solar cells because carrier recombination is harder. I have not done solar, so
Okay, fine, fine.
I'll leave this for.
Yeah. And so
Why solar coming here before the previous
maybe
ones?
some kind of a mishap, I think so. Are the submissions together or it's separate?
No, it's separate.
Okay, then.
This is on 13th.
Okay.
That is tomorrow, day after tomorrow. I don't know.
Okay.
8th would be a week after that, right?
So basically, one hint I can give you is that there is some E epsilon, K epsilon diagrams are there. Epsilon K or K epsilon quantum diagrams are there. For direct
Mhm.
band gap material, so this is how it would look like. That is conduction
Correct.
bands
E
minimum, yeah,
versus K diagram, right?
yeah,
EK
EK
diagram.
diagram. So this will be aligned. But in an
Correct. That
indirect,
I know.
yeah, so
Mm.
it will be like misaligned. And this misalignment is
Correct.
actually good because it makes recombination harder.
Correct.
Yeah.
But solar it will be used then. I don't know
Yeah, it
about
can be
solar.
used in solar. Yeah. Basically, what happens is that in solar cells, there is a light active material. You incident light on it, it creates electron hole pairs. And when you give a bias across that circuit, these electron hole pairs will be separated. Because of that, a current flows in the external circuit.
Yeah, I'll do solar
Yeah,
tonight and then answer
yeah, yeah.
this. Yeah, it's only a one lecture, right? So
Yeah,
I'll do that.
just a
Okay,
PN,
next
a
one.
modified PN junction. That's all.
Okay.
Yeah.
Which of the following items describe the emission mechanism of the light emitting diode? It is electroluminous.
Okay, wait. Which of the following terms emission light? Light emitting diode is, yeah, electroluminescence is correct. Yeah.
And which of the semiconductor is used for producing blue light?
There is a, yeah,
IN,
blue light
GaN, right?
LED, like a video has been
Gallium
uploaded.
nitride, I know something
Okay.
is used. So I'm thinking IN,
Yeah,
GaN is
yeah,
what the answer
yeah,
is. I know blue light, I think they got a Nobel Prize
yeah, yeah, yeah,
in 2014 or something very
yeah.
recently. It's there in the professor. So GAN was mentioned.
Mentioned. Okay.
So IN, I don't know. I'm just guessing that GAN is there on the only one. Yeah, 13th I can solve.
Yeah,
No
line width
problem.
equation I've already mentioned.
If you are given two LEDs, one is a blue and one is yellow, which of them
Will have larger line width. You'll have to decide based on the equation as well as the lambda
line
value.
lambda
Yeah.
value? Okay, so lambda, how do I get the lambda for yellow and blue?
You can assume it logically Vibgio, right? Yeah,
Uh.
from that.
There in the textbook it is there, I
Yeah.
think. There
Like
is
if
a
you,
lambda.
even if you don't know the exact value, you can logically apply it, which has largest, which has low, like smallest.
So it happens from high to low or low to high?
Uh, red has maximum, right? Yeah. Red has maximum wavelength, blue has least wavelength, or blue or violet. So Vibgio goes like that from minimum to maximum wavelength wise.
Oh,
Yeah.
okay, got it. I'll probably read something on this. Okay, the last one, which of the following recipients for efficient lasing action? Don't know. Okay, population inversion and total internal reflection.
Let me check. Yeah. And one more is there.
Lasing stimulated emission.
Yeah.
Yeah. Spontaneous is for LED. I know that.
Yeah.
Okay. Okay. I think
Yeah.
good. I with 50 questions is what for the whole of these
Yes.
eight,
Yeah. 50 questions, and
correct?
they've mentioned there will be questions from what do you call previously solved assignments, practice assignments, questions that are discussed in between class. That will be.
Okay.
And
Yeah, I read that.
yeah,
But where do I find all this content for the practice one?
practice assignment means whatever we are doing
I
now.
No, no, not that.
Then
There is in the questions here, right? When there is an assignment quiz, there is something called practice week
yeah, yeah, yeah.
7. So where do I find answers for that?
They just give the final answer. I don't think they'll upload a detailed one. Sometimes they do, but this time I didn't notice getting a.
Okay, if you can upload, if you have those questions somewhere solved,
Okay.
if you can upload in the shared drive, it will help.
Okay, yeah, yeah, I'll check. Like,
More to review the questions, right?
yeah.
You cannot solve
And one more
all the.
thing, if possible, I'll ask them to upload because those are prepared by another TA. So I don't have permission to upload that. So I'll,
Yeah, if
yeah,
you can check and if they
yeah,
give you only then
yeah, yeah.
please.
Okay, yeah, I'll check that. Yeah, sure.
Yeah. Okay,
Yeah,
thank you so
yeah.
much.
Thank you so much. Any other doubts you have?
There's a lot of reading to be done before
Okay, fine, fine,
doubts.
fine. So in case you get any doubts while solving, please do email
Yeah,
me.
yeah,
Yeah,
I'll update you.
yeah,
Thank you.
yeah. Okay, I think if that's the case, then it's done for today. Thank you for joining. And somebody just joined in the last 10 minutes. May I know who that is? Okay, I didn't get that part. Somebody joined, right? What is her name? Dr. Helen Marina. Yeah, thank you so much. Miss like Helen, you joined. Like the session actually starts at 7. So I hope you have gone through the videos or anything. So if you have any doubts, my mail ID is there in the initial few videos. I've projected my mail ID. So you can just mail me if you have any doubts or queries regarding the assignment so I can get back to you. So is that okay? I think, okay. Yeah, she has
Yeah,
input it.
thank you.
Yeah, thank you so much. Yeah. Yeah, you can speak, Miss Helen. Yeah.
Yes, ma'am. I will follow the previous
Yeah,
videos.
yeah, yeah. And can you we are moving towards the last two sessions of this section. So please go through all the videos and wherever you get doubts, you can either ask in the next class or you can just mail me. Either will work.
Okay, ma'am.
Yeah.
Okay,
Okay.
ma'am.
Okay. Thank you so much for joining. Yeah.
Thank you.
Yeah. Yeah. You guys can leave now. Thank you so much.